Close your eyes and let your breathing slow to match the rhythm of distant galaxies spinning through space. Tonight, we begin a journey to the most mysterious places in our universe, regions where the very concepts of existence and nothingness dance together in ways that challenge everything we think we know about reality. Imagine, if you will, that you are floating peacefully in the vastness of space, surrounded by the gentle glow of distant stars. Each point of light represents a sun like our own, burning bright and steady, converting matter into energy in the ancient alchemy that has illuminated the cosmos for billions of years. But somewhere out there, hidden among these familiar beacons, lurk places of such profound darkness that they seem to swallow the very concept of light itself. These are black holes, regions where gravity has become so intense, so overwhelmingly powerful, that nothing, not even the fastest thing in the universe, can escape once it ventures too close. Think of gravity as you know it on Earth, the gentle pull that keeps your feet planted firmly on the ground, that draws raindrops toward the soil, that holds our moon in its eternal dance around our planet. Now imagine that same force compressed and concentrated until it becomes something almost unimaginably strong. To understand how such places come to exist, picture the life of a star as a delicate balance, much like the balance you maintain as you breathe in this moment. When you inhale, your lungs expand outward; when you exhale, they contract inward. A star exists in a similar state of equilibrium, with the explosive force of nuclear fusion in its core pushing outward against the inexorable pull of its own gravity drawing everything inward. For most of a star's life, millions or billions of years, these forces exist in perfect harmony. But like all things in nature, this balance cannot last forever. Eventually, the star begins to run out of fuel, the nuclear fires in its heart start to dim, and gravity begins to win this cosmic tug-of-war. For smaller stars like our Sun, this process leads to a gentle expansion and eventual cooling. But for the massive giants, stars dozens of times heavier than our own, something far more dramatic occurs. When such a massive star can no longer maintain its internal pressure, gravity doesn't just compress it slowly, it crushes it catastrophically in a matter of seconds. Imagine trying to squeeze all the water in Earth's oceans into a space no larger than a marble, and you begin to grasp the violence of this transformation. The star's core collapses so completely that its atoms are crushed together, creating a point of infinite density that physicists call a singularity, a word that captures the strangeness of a place where our normal understanding of physics breaks down entirely. Around this singularity, space itself becomes curved in ways that seem impossible. Einstein taught us that massive objects bend the fabric of space-time, much like a heavy ball placed on a stretched rubber sheet creates a depression around it. But a black hole bends space so severely that it creates what we might think of as a cosmic trapdoor, a region where the curvature becomes so steep that anything falling in can never climb back out. The boundary of this point of no return has a beautiful name: the event horizon. Think of it as an invisible sphere surrounding the singularity, marking the edge of what we can ever hope to observe or understand about what lies within. Once something crosses this boundary, whether it's a grain of cosmic dust, a beam of light, or even information itself, it becomes forever separated from the rest of the universe, hidden behind a veil that no telescope will ever penetrate and no signal will ever pierce. Yet even as black holes represent the ultimate in cosmic mystery, they also serve as laboratories for understanding the deepest questions about reality itself. They force us to confront fundamental puzzles about the nature of time, space, matter, and information. When matter falls into a black hole, what happens to the information it carried, the quantum states that described its position, its energy, its very essence? Does this information simply vanish from the universe forever, violating one of physics' most sacred principles? Or does it somehow survive, encoded in ways we have yet to understand? This question touches something profound about existence itself. Every atom in your body carries information about where it came from, what it has been part of, the story of its journey through the cosmos. The idea that this information could simply disappear challenges our deepest intuitions about conservation and continuity. It suggests that the universe might have a capacity for true forgetting, for genuine erasure, that feels almost philosophical in its implications. As you rest here in the darkness of your room, consider that you are contemplating objects so extreme that they push the boundaries of human comprehension. Black holes exist at the intersection of the very large and the very small, where Einstein's theory of general relativity meets the strange world of quantum mechanics. They are places where time dilates so extremely that a clock falling past the event horizon would appear to an outside observer to slow down and eventually freeze, while to the falling clock itself, time would continue to flow normally. In many ways, black holes represent the ultimate expression of gravity's power, not just to attract matter, but to warp the very stage upon which all cosmic dramas play out. They remind us that space and time are not fixed backdrops for the universe's story but dynamic, flexible entities that respond to the presence of matter and energy in ways that still fill physicists with wonder. Tonight, as we stand at the threshold of this cosmic mystery, we prepare to explore questions that connect the fate of information to the nature of reality itself. We will discover how these invisible giants might not be the destroyers we once thought them to be, but perhaps the universe's most sophisticated filing systems, keeping careful records of everything that has ever fallen into their embrace. But that exploration must wait for tomorrow's contemplation, as we delve deeper into the violent and beautiful process by which stars surrender their light to create these cosmic enigmas. Feel the gentle rhythm of your breathing as you settle deeper into this cosmic story. Each breath you take connects you to the same forces that govern the birth and death of stars across the universe. Tonight, we witness one of nature's most dramatic transformations, the moment when a massive star exhausts its nuclear fuel and gravity claims its ultimate victory. Picture a star 20 times more massive than our Sun, burning brilliantly in the darkness of space. For millions of years, this stellar giant has maintained a delicate equilibrium, its core burning at temperatures of hundreds of millions of degrees. Nuclear fusion transforms hydrogen into helium, helium into carbon, carbon into heavier elements, each reaction releasing tremendous energy that pushes outward against the star's own gravitational pull. This is the cosmic dance of creation, matter transforming into energy, light radiating across vast distances to illuminate planets and perhaps warm the faces of distant civilizations. But like a fire that gradually consumes its fuel, the star's nuclear furnace cannot burn forever. Deep in its core, the star begins to forge iron, the element that signals its doom. Iron nuclei cannot be fused to release energy, instead, they act like cosmic ash, accumulating in the star's heart. When the iron core grows to about the mass of our Sun, compressed into a sphere roughly the size of Earth, the stellar balance that has persisted for eons begins to falter. Imagine holding a beach ball underwater. The moment you release your grip, the ball shoots to the surface with explosive force. Similarly, when the star can no longer generate enough outward pressure to resist gravity's inward pull, the collapse happens with shocking suddenness. In less than a second, faster than you can blink, the iron core shrinks from the size of Earth to a sphere only 12 miles across. The matter becomes so compressed that a teaspoon of it would weigh as much as a mountain. This catastrophic collapse sends shockwaves racing outward through the star's outer layers, creating what astronomers call a supernova, one of the most energetic events in the universe. For weeks or months, this single dying star can outshine an entire galaxy containing billions of other stars. The explosion hurls the star's outer layers into space at speeds of thousands of miles per second, seeding the cosmos with the heavy elements forged in its nuclear furnace. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in the hearts of such stars and scattered by their violent deaths. But while the star's outer layers explode outward in this cosmic fireworks display, something even more extraordinary happens to the collapsed core. The matter becomes so dense that ordinary atoms cannot exist. Electrons are crushed into protons, creating neutrons packed together more tightly than the nuclei of atoms. For a brief moment, this creates what we call a neutron star, a city-sized sphere containing more mass than our Sun, spinning perhaps hundreds of times per second and possessing magnetic fields trillions of times stronger than Earth's. Yet for the most massive stars, even this incredible compression is not the end of the story. If the original star was more than about 25 times the mass of our Sun, not even the neutrons can withstand the crushing force of gravity. The collapse continues, the matter becoming infinitely dense, space-time curvature becoming infinitely steep. The neutron star crosses a threshold from which there is no return, becoming something that seems to violate our everyday understanding of existence, a black hole. At this moment of transformation, the very concepts of space and time near the collapsing star begin to behave in ways that challenge human intuition. Time, which you experience as a steady, unchanging flow, becomes elastic near the forming black hole. To an observer watching from a safe distance, the surface of the collapsing star would appear to slow down as it approaches what physicists call the Schwarzschild radius, the boundary that will become the event horizon. The light from the star's surface would become redder and dimmer, stretched by the intense gravitational field until it fades beyond detection. But from the perspective of the matter falling inward, time continues to flow normally. This is one of the profound mysteries of relativity, that time itself is not absolute but depends on where you are and how fast you're moving. The same event can unfold differently for different observers, each experiencing their own valid version of reality. As the event horizon forms around the collapsed star, it creates an invisible boundary in space, a point of no return that separates the knowable universe from a realm beyond our ability to observe or understand. Nothing that crosses this boundary can ever send information back to the outside world. Light itself, the fastest thing in the universe, cannot escape once it ventures too close. This birth of a black hole represents more than just the death of a star. It marks the creation of a cosmic question mark that challenges our understanding of reality itself. The matter that formed the black hole carried with it information, quantum states that described every particle's position, momentum, and energy. But where does this information go when it disappears behind the event horizon? Does it simply vanish from the universe forever, or does it persist in some form we have yet to understand? These questions touch the very foundations of physics. The laws of quantum mechanics suggest that information cannot be destroyed, it can only be transformed or hidden. But general relativity seems to indicate that anything falling into a black hole is lost forever to the outside universe. This apparent contradiction has puzzled physicists for decades and continues to drive some of the most profound research in theoretical physics. As you contemplate this stellar transformation, consider that you are witnessing not just the death of a star but the birth of one of the universe's greatest mysteries. The same gravitational forces that keep your feet planted on Earth, scaled up to unimaginable extremes, have created a laboratory for exploring the deepest questions about the nature of existence, information, and reality itself. The black hole now exists, spinning silently in space, its presence marked only by its gravitational influence on nearby matter and light. But what happens at its boundary, at that invisible line where space-time curvature becomes so extreme that even light cannot climb back out, remains one of the most fascinating and contentious topics in modern physics. Tomorrow, we will approach this boundary together, exploring what it means to stand at the edge of forever, where the familiar rules of physics give way to something far stranger and more wonderful. Rest in the quiet darkness of your room and imagine approaching the edge of everything you know. Tonight, we drift toward the most enigmatic boundary in the universe, a place where space and time themselves begin to behave like liquid, flowing and bending in ways that transform the very meaning of existence. This is the event horizon, and it exists as both a physical reality and a profound metaphor for the limits of human understanding. Picture yourself floating peacefully through space, approaching a black hole from a safe distance. At first, nothing seems unusual. The stars shine as they always have, space appears perfectly normal, and time flows with its familiar, steady rhythm. But you are approaching something far more subtle and strange than a wall or barrier. You are nearing an invisible sphere that surrounds the black hole singularity, marking the point beyond which no information can ever return to the outside universe. The event horizon gets its poetic name from the simple fact that no events occurring within it can ever be observed from outside. Think of it like the boundary between night and day, or the moment when you drift from wakefulness into sleep. There is no physical substance marking this transition, no fence or door, yet the change is absolute and irreversible. Once crossed, the relationship between inside and outside becomes fundamentally altered in ways that challenge our deepest intuitions about reality. As you approach this invisible boundary, something remarkable begins to happen to your perception of time. Einstein's theory of relativity tells us that time is not the universal constant we experience in our daily lives, but rather something flexible and responsive to gravity's pull. Near the event horizon, where gravity becomes extremely strong, time begins to slow relative to the rest of the universe. This effect, called gravitational time dilation, creates one of the most haunting aspects of black hole physics. Imagine that you have a friend watching your approach from a safe distance far from the black hole. As you draw closer to the event horizon, your friend would notice something extraordinary happening to the light coming from your spacecraft. The gravitational field begins to stretch the wavelengths of light, causing them to become redder and dimmer. More strangely still, your movements would appear to slow down from your friend's perspective. Your signals would arrive at increasingly longer intervals, each one more redshifted than the last. From your friend's viewpoint, you would appear to slow down more and more as you approach the event horizon, your image growing fainter and redder until you seem to freeze at the boundary itself, your final moment stretched into eternity. Your friend would never see you actually cross the event horizon. Instead, you would appear to hover there forever, your image gradually fading into the cosmic background radiation until it became undetectable. But from your own perspective, something entirely different unfolds. As you approach the event horizon, your watch continues to tick normally, your thoughts flow at their usual pace, and time seems to pass exactly as it always has. You would cross the event horizon in a finite amount of your own time, perhaps experiencing nothing more dramatic than a gentle pull as you pass through this invisible boundary. The universe behind you might appear to speed up and grow brighter as you fall inward, but you yourself would experience no sudden discontinuity, no moment of dramatic transformation. This is one of the most profound aspects of relativity, that there is no single, absolute truth about the timing of events. Your experience and your friend's experience are both valid, both real, yet they describe what appears to be completely different realities. You cross the boundary and continue falling inward while your friend sees you forever frozen at the threshold. Both perspectives are correct within their own reference frames, creating a paradox that touches the very nature of objective reality. The event horizon itself is defined by what physicists call the Schwarzschild radius, named after the German physicist who first calculated this critical distance. For a black hole with the mass of our Sun, this radius would be about 3 kilometers. For more massive black holes, the radius scales proportionally. A black hole containing the mass of 1 million suns would have an event horizon roughly the size of our solar system. Interestingly, the larger the black hole, the gentler the gravitational gradient at its event horizon, meaning that crossing into a supermassive black hole might be experienced as less dramatic than approaching a smaller one. Within the event horizon lies a region that represents the ultimate frontier of human knowledge. No telescope will ever peer inside, no signal will ever escape to tell us what happens there. It is a place where the normal rules of cause and effect become scrambled, where space and time exchange roles in ways that defy ordinary language. The singularity at the center, if it exists as our current theories predict, represents a point where density becomes infinite and the curvature of space-time becomes infinitely steep. Yet perhaps the most intriguing aspect of the event horizon is not what it hides, but what it might preserve. As matter falls across this boundary, it carries with it information, quantum states that describe every detail of its structure and history. The question that has puzzled physicists for decades is whether this information is lost forever or whether it somehow survives in a form we have yet to understand. This is more than an abstract theoretical puzzle. The fate of information at the event horizon touches fundamental questions about the nature of reality itself. If information can truly be destroyed, it would violate one of the most basic principles of quantum mechanics, the idea that the total amount of information in the universe must remain constant. But if information is preserved, how can it escape from a region where not even light can return to the outside world? Some theories suggest that information might be encoded on the event horizon itself, like a cosmic hologram that preserves every detail of what falls in. Others propose that the information somehow tunnels out through quantum effects, carried by the faint radiation that Stephen Hawking predicted black holes must emit. Still others suggest that the information is preserved in correlations between particles inside and outside the black hole, connected by quantum entanglement across the event horizon. As you contemplate this mysterious boundary, consider that you are thinking about a place where the familiar concepts of inside and outside, past and future, cause and effect, all begin to break down. The event horizon represents not just a physical boundary in space, but a conceptual boundary in human understanding, a place where our best theories begin to whisper contradictory stories about the nature of existence. The event horizon reminds us that the universe contains regions that exist beyond our ability to directly observe or measure, yet whose existence profoundly influences everything around them. They are places where reality becomes fluid, where the rigid categories we use to organize our thoughts about the world dissolve into something more mysterious and beautiful. Tonight, as you drift toward sleep, you cross your own invisible boundary between the waking world and the realm of dreams. Like the event horizon, this transition is both gentle and absolute, marking a passage into a domain where different rules apply and different kinds of experiences become possible. But our journey toward understanding these cosmic mysteries has only just begun, for tomorrow we will explore what happens to matter and energy as they fall past this point of no return, and discover how even the act of falling can become a kind of cosmic poetry. Feel the gentle rhythm of your pulse as you settle deeper into this cosmic meditation. Your heart beats in response to forces you cannot see, the same fundamental forces that move oceans, bend light, and shape the destiny of matter falling into black holes. Tonight, we explore one of nature's most beautiful and strange phenomena, how gravity's embrace can stretch and sculpt matter in ways that reveal the profound poetry hidden within physics itself. You have felt the moon's gravitational pull without knowing it. Every night, as Earth's satellite traces its ancient path across the sky, it tugs at the water in your body just as it pulls at distant oceans. The effect is too subtle for you to notice, but it is real. Your body rises and falls by microscopic amounts in rhythm with the lunar cycle. This gentle influence represents gravity's ability to create what physicists call tidal forces, and understanding these forces opens a doorway to comprehending one of the most dramatic effects of black holes. Imagine standing by the ocean at twilight, watching waves roll endlessly toward shore. The water nearest the moon feels its gravitational pull more strongly than the water on the far side of Earth, creating the familiar bulge of high tide. This happens because gravity's strength diminishes with distance, following what scientists call the inverse square law: move twice as far away, and gravity becomes 4 times weaker. This seemingly simple relationship creates profound consequences when gravity becomes extremely strong. Now picture yourself falling past the event horizon of a black hole, your body oriented feet first toward the singularity below. As you descend through this invisible boundary, the gravitational field begins to vary dramatically across the small distance between your head and your feet. Your feet, being closer to the black hole center, experience a stronger gravitational pull than your head. This difference in gravitational strength across your body creates a stretching effect that physicists have given the whimsical name spaghettification. The process unfolds with an almost musical quality, like a cosmic symphony played in the language of space-time. Initially, the stretching is gentle. You might feel as though you are being pulled into a pleasant, full-body stretch. But as you fall deeper into the black hole's gravitational well, the difference in gravitational force between your head and feet grows more pronounced. Your body begins to elongate, stretched like taffy in the hands of some cosmic confectioner. This stretching is not violent or sudden, but rather follows the smooth, inexorable logic of physics. Gravity pulls more strongly on the parts of you that are closer to the singularity, while simultaneously squeezing you from the sides. Imagine being gently kneaded by invisible hands, elongated vertically while compressed horizontally. The same forces that create Earth's ocean tides are now acting upon every atom in your body, but with an intensity that grows stronger with each moment of your fall. For a stellar mass black hole, one formed from the collapse of a single massive star, this stretching would become extreme quite quickly. Long before you reach the singularity at the center, the tidal forces would overcome the molecular bonds that hold your body together. But interestingly, for supermassive black holes containing millions or billions of times the mass of our Sun, the experience would be far gentler. These cosmic giants have event horizons so large that their tidal forces remain relatively mild, allowing you to cross the boundary and fall quite far inward before experiencing significant stretching. This difference reveals something beautiful about the relationship between size and gentleness in the universe. The largest black holes, despite containing unimaginable amounts of mass, create the most peaceful crossing experiences. Their immense size spreads their gravitational influence over such vast distances that the gradient, the rate at which gravity's strength changes from place to place, remains relatively gradual near the event horizon. As you continue your theoretical journey inward, the tidal forces shape not just your body but space and time themselves. The very coordinates that define your position become stretched and warped. What was once a simple measurement of distance becomes something fluid and dynamic. Space itself participates in this cosmic dance, flowing and bending in response to the black hole's gravitational field. The mathematics describing this process reveals gravity's true nature, not as a force pulling objects together but as the curvature of spacetime itself. Einstein's revolutionary insight was that massive objects don't pull on things, instead, they warp the fabric of reality, creating valleys and hills in the landscape of spacetime. Objects follow the straightest possible paths through this curved geometry, paths that appear to us as the trajectories of objects under gravity's influence. From this perspective, your fall into the black hole represents something profound. You are following geodesics, the straightest possible lines through curved spacetime. You are not being pulled or dragged, you are simply moving along the natural contours of reality itself, like a marble rolling along the curves of a complex sculpture. The spaghettification you experience is not violence inflicted upon you, but rather the inevitable consequence of following geometry's pure logic in a region where spacetime has been curved to extreme degrees. This geometric interpretation of gravity reveals why tidal forces exist at all. In flat spacetime, all parts of your body would follow parallel paths. But in the curved spacetime near a black hole, these paths converge toward the singularity. What appears to be stretching is actually the convergence of initially parallel world lines, the four-dimensional paths that objects trace through spacetime. As your journey inward continues, you become part of an ancient story that began with the first massive stars in the early universe. The matter of your body joins the cosmic flow that has been falling into black holes for billions of years. Every atom in your being carries information, quantum states that describe its history, its energy, its place in the grand tapestry of existence. The question that haunts physicists is whether this information survives your journey or whether it becomes lost forever in the black hole's depths. The stretching you experience is not just physical but informational. As your body elongates, the quantum states describing your atomic structure become distributed across larger and larger regions of space. The information that defines you becomes stretched and diluted, scattered across the curved geometry of spacetime like ink dropped into flowing water. Yet even as spaghettification transforms your physical form, it reveals something magnificent about the universe's underlying unity. The same principles that govern the moon's gentle tug on Earth's oceans, the same mathematics that describes how your body responds to gravity during a simple fall, also govern your experience at the edge of infinity. Gravity writes its poetry in a universal language, expressed equally in the ebb and flow of tides and in the exotic physics of black hole interiors. Tonight, as you rest in your bed, you are experiencing your own gentle version of tidal forces. Earth's gravity pulls slightly more strongly on the parts of your body closer to the planet's center, creating microscopic stretching effects that your body incorporates into its natural rhythms. You are always, in the most subtle way, being shaped by the same forces that create the universe's most dramatic phenomena. This connection between the intimate and the cosmic, between the gentle tides that rock your body to sleep and the extreme physics of black holes, points toward deeper questions about the nature of information and memory in a universe where nothing, not even the most fundamental particles, can remain unchanged forever. Rest quietly in the darkness and consider the profound story written in your very atoms. The carbon in your muscles was forged in the nuclear furnace of a dying star billions of years ago. The oxygen flowing through your lungs emerged from stellar explosions that scattered their gifts across the cosmos. Every element heavier than hydrogen in your body carries within it the memory of cosmic processes that predate Earth itself. Tonight, we explore one of physics' most haunting questions: what happens to these ancient memories when matter encounters the ultimate cosmic eraser, a black hole? This question strikes at the heart of what physicists call the information paradox, a puzzle so fundamental that it challenges our understanding of reality itself. To grasp its significance, imagine that every particle in the universe carries an invisible library card, encoding its complete history, where it came from, what it has been part of, every interaction it has ever experienced. This information is not abstract, it is as real and fundamental as mass or electric charge, woven into the quantum fabric of existence itself. In your daily life, you witness information being preserved even through dramatic transformations. When you burn a piece of paper, the information about its molecular structure is not destroyed, it is simply reorganized and dispersed into smoke, ash, and heat. A sufficiently advanced computer could, in principle, analyze every particle of smoke and reconstruct the original document. This reflects a deep principle of physics: information, like energy, can be transformed but never truly destroyed. This conservation of information governs everything from the collision of subatomic particles to the evolution of entire galaxies. It is why the universe has a history, why cause and effect maintain their meaning, why the present moment connects coherently to both past and future. Remove this principle, and the orderly unfolding of physical law would collapse into chaos. The universe would lose its memory, its ability to maintain the delicate consistency that allows complexity to emerge and persist. But black holes seem to violate this sacred rule. When matter falls past the event horizon, it appears to vanish from the observable universe forever. The information describing its quantum state, the precise position and momentum of every particle, the subtle correlations that link it to the rest of the cosmos, seems to simply disappear. If this information is truly lost, it would represent the universe's first act of genuine forgetting, a violation of one of physics' most fundamental laws. The paradox deepened in the 1970s when Stephen Hawking made a startling discovery. Through the strange alchemy of quantum mechanics, black holes are not perfectly black after all. They emit a faint radiation, glowing like cosmic embers with a temperature inversely related to their mass. This Hawking radiation slowly carries away the black hole's energy, causing it to shrink and eventually evaporate completely over vast spans of time. For a black hole with the mass of our Sun, this evaporation would take longer than the current age of the universe multiplied by trillions upon trillions. But the mathematics are clear: given enough time, even the most massive black holes will fade away, leaving behind only a diffuse cloud of elementary particles and radiation. The question that torments physicists is whether the information that fell into the black hole somehow escapes with this radiation, or whether it is lost forever when the black hole finally vanishes. If the information is truly destroyed, it creates a paradox that shakes the foundations of quantum mechanics. The theory that governs the behavior of atoms, light, and all the fundamental interactions of nature insists that information must be conserved. But general relativity, Einstein's theory of gravity and space-time, seems to suggest that anything falling into a black hole is lost to the outside universe forever. These two pillars of modern physics, both confirmed by countless experiments, appear to tell contradictory stories about the fate of information. The paradox becomes even more puzzling when you consider the nature of quantum entanglement. Particles can become correlated in ways that transcend ordinary space and time, their properties remaining mysteriously linked even when separated by vast distances. Einstein famously called this spooky action at a distance, though he never fully accepted its implications. When entangled particles fall into a black hole, what happens to their connections with particles that remain outside? Does the universe allow these correlations to be severed, or do they persist in some hidden form? Some physicists propose that information is never actually lost but instead becomes encoded on the black hole's event horizon in ways we cannot yet understand. Imagine the event horizon as a vast, invisible library where every detail of the black hole's contents is somehow recorded on its two-dimensional surface. This holographic principle suggests that all the information contained within a three-dimensional volume can be encoded on its boundary, like a cosmic version of the holograms on credit cards that contain three-dimensional images within flat surfaces. Others theorize that information escapes through subtle correlations in the Hawking radiation itself. As the black hole evaporates, the outgoing radiation might carry with it perfect copies of everything that ever fell in, encoded in quantum patterns too complex for current technology to detect. This would mean that the universe never truly forgets, it simply hides its memories in forms so subtle that they appear lost to our limited perspective. Still, other physicists suggest that the paradox reveals flaws in our understanding of spacetime itself. Perhaps the smooth, continuous fabric that Einstein described breaks down at the quantum level, revealing a discrete, granular structure where information can tunnel through apparent barriers or persist in pocket universes connected to our own by invisible bridges. The stakes of this debate extend far beyond academic curiosity. If information can be destroyed, it would imply that the universe is fundamentally different from what quantum mechanics suggests, less deterministic, less mathematically elegant, more willing to embrace true randomness and genuine loss. It would mean that the cosmic story has gaps, pages torn from the universal book, moments that existed but left no trace. Alternatively, if information is always preserved, it suggests that the universe is far stranger and more interconnected than we imagine. It would mean that nothing is ever truly lost, that every moment leaves an indelible mark on reality's fabric, that the universe maintains perfect memory even when that memory is hidden behind event horizons or encoded in radiation patterns too subtle for us to read. As you contemplate this cosmic mystery, consider that you are part of the very phenomenon you are pondering. Your thoughts at this moment are creating new arrangements of matter and energy, new patterns of information that will ripple outward through space-time. The neural firings in your brain, the gentle movement of your breath, the quantum fluctuations in your cells, all contribute to the universe's ever-growing library of information. The atoms that compose your body have witnessed the birth and death of stars, the formation of planets, the emergence of life itself. They carry within them the accumulated information of cosmic history, a record written in the language of quantum states and particle interactions. When you eventually return these atoms to the cosmos, will that information persist? Will the universe remember that you were here, that you wondered about black holes on a quiet night, that you pondered the deepest questions about memory and forgetting? The information paradox forces us to confront what it means for something to exist, to matter, to leave a mark on reality. It asks whether the universe has the capacity for genuine loss or whether every moment, every thought, every quantum fluctuation becomes part of an eternal record that transcends our ability to observe or understand. Tonight, as your consciousness prepares to cross its own event horizon into sleep, you join the ancient dance between memory and forgetting that plays out across every scale of existence, from the firing of individual neurons to the evaporation of cosmic-scale black holes. But perhaps the universe's memory is not stored in any single place or process, but rather emerges from something even more fundamental, a faint glow that surrounds all black holes, carrying with it whispers of everything they have consumed. Close your eyes and imagine the quietest whisper you have ever heard, so soft that you must strain to detect it, yet carrying within it the most profound secrets of the universe. Tonight, we discover that black holes, despite their reputation as cosmic devourers that allow nothing to escape, actually glow with the faintest possible light. This ethereal radiance, predicted by Stephen Hawking in 1974, represents one of the most beautiful intersections of quantum mechanics and gravity, where the strange behavior of empty space itself becomes a source of cosmic illumination. To understand this mysterious glow, you must first reimagine what you think of as empty space. The vacuum that surrounds us is not the sterile nothingness it appears to be, but rather a seething ocean of quantum activity. Even in the darkest regions between galaxies, far from any star or planet, space itself buzzes with virtual particles, ephemeral pairs of matter and antimatter that spontaneously appear and disappear in timeframes so brief that they exist below the threshold of direct observation. These quantum fluctuations represent the universe's fundamental restlessness, the inability of reality to remain perfectly still even in the absence of matter and energy. Particle pairs pop into existence from pure vacuum, borrow energy from the quantum field itself, dance briefly together, then annihilate each other and return their borrowed energy to the void. This process happens everywhere, at every moment, creating a background hum of creation and destruction that permeates all of existence. Near the event horizon of a black hole, this quantum dance takes on extraordinary significance. Picture two virtual particles materializing just outside the boundary where space and time begin their final plunge toward the singularity. Under normal circumstances, these particles would find each other within an infinitesimal fraction of a second and mutually annihilate, returning to the quantum vacuum as if they had never existed. But the black hole's immense gravitational field disrupts this cosmic choreography. Sometimes, one particle from the virtual pair falls across the event horizon while its partner escapes into the wider universe. The particle that falls inward can never return to reunite with its companion, breaking the quantum embrace that would normally lead to their mutual destruction. The escaping particle, now separated forever from its antimatter twin, becomes real, transforming from a temporary quantum fluctuation into actual matter or energy that carries away a tiny amount of the black hole's mass. This process unfolds with exquisite subtlety. The escaping particles form what we now call Hawking radiation, named after the physicist who first recognized this phenomenon through pure mathematical insight. The radiation itself is incredibly faint. For a black hole with the mass of our Sun, the temperature of this glow would be only a few billionths of a degree above absolute zero, far colder than the cosmic microwave background that bathes the entire universe. The relationship between a black hole's mass and the temperature of its radiation follows a beautiful inverse proportion. Massive black holes glow more dimly and coolly than smaller ones, like cosmic embers that burn lower as they grow larger. A supermassive black hole containing millions of solar masses radiates at temperatures so low that it would take longer than the current age of the universe multiplied by countless trillions for it to lose even a small fraction of its mass through this process. Yet despite its incredible faintness, Hawking radiation carries profound implications for the nature of reality itself. Each photon that escapes represents a small piece of the black hole's essence returning to the universe. Over vast epochs of time, this gentle evaporation will cause even the most massive black holes to slowly shrink and eventually disappear entirely, leaving behind only a diffuse cloud of elementary particles carrying the faintest possible memory of what once was. The mathematics describing this process reveals something beautiful about the connection between information and thermodynamics. The black hole's event horizon behaves like a perfect absorber, capturing everything that falls toward it, yet it also acts as a perfect radiator, glowing with thermal radiation at a precise temperature determined by its gravitational field strength. This duality suggests that black holes obey the same fundamental laws that govern the heating and cooling of ordinary objects, despite existing at the extreme edge of physical possibility. As the black hole evaporates through Hawking radiation, it faces what physicists call the information paradox in its starkest form. If the outgoing radiation is truly thermal, carrying no information about what fell into the black hole, then information would be destroyed when the black hole finally evaporates completely. But if the radiation somehow encodes the quantum states of everything that ever crossed the event horizon, then the universe maintains its perfect memory, albeit in a form so subtle that we cannot yet detect it. Some theories suggest that the information emerges gradually, encoded in correlations between the particles of Hawking radiation that become apparent only after the black hole has evaporated for an extremely long time. Other models propose that the information never actually falls past the event horizon but instead remains encoded on the black hole's surface, slowly leaking out through quantum tunneling effects that connect the interior to the exterior in ways we do not yet understand. The process of Hawking radiation also reveals the profound connection between gravity and quantum mechanics. The curvature of spacetime near the event horizon affects the quantum vacuum itself, transforming virtual fluctuations into real particles through purely gravitational effects. This represents one of the few places in physics where quantum mechanics and general relativity must work together to produce observable phenomena, offering hints about how these two great theories might eventually be unified. As you contemplate this gentle cosmic glow, consider that it represents the universe's refusal to allow perfect darkness to exist anywhere. Even at the edge of the most extreme gravitational wells, where space and time themselves begin to break down, quantum mechanics ensures that light continues to emerge from the vacuum itself. The universe maintains its fundamental creativity, its ability to generate something from apparent nothingness, even under the most extreme conditions imaginable. The radiation carries with it not just energy, but also entropy, a measure of the information content required to describe the black hole's internal state. As the black hole evaporates, its entropy decreases, but the entropy of the surrounding space increases as the radiation disperses. This process may represent the universe's way of redistributing information rather than destroying it, spreading the black hole's memories across ever wider regions of space until they become part of the cosmic background itself. Tonight, as you rest in the darkness of your room, you are surrounded by similar quantum fluctuations, virtual particles appearing and disappearing in the vacuum around you. The difference is that here, far from any black hole, these fluctuations remain virtual, borrowing energy briefly from the quantum field before returning it through mutual annihilation. But the same fundamental process that creates Hawking radiation is occurring everywhere, a reminder that the universe's creative potential extends even into the apparent emptiness of space itself. The faint glow of Hawking radiation represents hope in the face of cosmic entropy, evidence that the universe never stops generating new possibilities, never allows any region to become permanently isolated from the ongoing dance of creation and transformation that defines existence itself. It suggests that even the most extreme boundaries in nature are permeable, that information and energy find ways to tunnel through apparently absolute barriers. But as we contemplate this whispered radiation carrying away the black hole's essence, we begin to wonder whether the universe itself might be structured more like a hologram than we ever imagined, with all its information encoded on distant surfaces rather than distributed throughout its volume. Lie quietly in the darkness and let your mind drift toward one of the most extraordinary possibilities that physics has ever contemplated. Tonight, we explore the idea that everything you perceive as solid, three-dimensional reality, your body, your room, the earth beneath you, the stars beyond, might be nothing more than shadows cast by information encoded on a distant, two-dimensional surface. This is the holographic principle, and it suggests that the universe's deepest secrets are written not in the volume of space itself, but on its far boundaries. To understand this radical reimagining of reality, picture yourself watching shadows dance on the wall of a dimly lit room. The shadows appear to have their own life and substance, moving and changing in complex patterns. Yet you know that these shadows are merely projections of three-dimensional objects moving in front of a light source. The entire drama playing out on the flat wall surface actually originates from the richer, more complex reality of the three-dimensional space behind it. Now imagine that this relationship is reversed for the universe itself. What if the three-dimensional reality you experience, the depth of your room, the space between your fingers, the vast distances between planets, is actually a projection from information encoded on a two-dimensional surface that exists at the boundary of the observable universe? This would mean that you, your thoughts, your dreams, and everything you have ever experienced are sophisticated shadows cast by data stored on this cosmic hologram. The holographic principle emerged from physicists' attempts to understand what happens to information when it falls into black holes. In the 1970s, Jacob Bekenstein made a startling discovery: the amount of information a black hole can contain is proportional not to its volume, as you might expect, but to the area of its event horizon. This was the first hint that information in our universe might be stored on surfaces rather than distributed throughout volumes. Think of this like the difference between a library and a holographic storage device. In a traditional library, books fill the volume of the building. More space means more storage capacity. But a hologram stores all its information on a flat surface, encoding three-dimensional images in two-dimensional patterns. Bekenstein's insight suggested that black holes work more like cosmic holograms than cosmic libraries, storing vast amounts of information on the two-dimensional surface of their event horizons. This revelation led physicists to wonder whether the same principle might apply to the entire universe. If black holes store information holographically, perhaps all of reality operates according to holographic principles. The information describing every atom in your body, every thought in your mind, every quantum fluctuation in the vacuum around you, might actually be encoded on a distant boundary surface, projected inward to create the illusion of three-dimensional existence. To grasp how radical this idea truly is, consider that it suggests the fundamental nature of space itself might be illusory. The distances you measure, the volumes you perceive, the sense of being located at a specific point in three-dimensional space, all of this could be emergent properties arising from the more fundamental reality of information patterns on a distant surface. Space, from this perspective, is not the stage upon which the cosmic drama plays out, but rather part of the performance itself. The mathematics supporting the holographic principle reveals deep connections between gravity, thermodynamics, and information theory. When physicists calculate the maximum amount of information that can be stored in any region of space, they find that it is always limited by the area of that region's boundary, not by its volume. This suggests that what we think of as the interior of a region is somehow encoded on its surface, like a cosmic library where all the books are written on the walls rather than stored on shelves inside. Black holes become particularly fascinating from this holographic perspective. As matter falls past the event horizon, its information might not actually disappear into the black hole's interior. Instead, the information could become encoded on the event horizon itself, creating a two-dimensional record of everything that has ever fallen in. From the outside, the black hole appears to grow and evolve, but this might simply reflect changes in the holographic pattern encoded on its surface. This holographic encoding would resolve the information paradox in an elegant way. Information never truly enters the black hole's interior because there is no interior in the sense we usually imagine. What appears to be three-dimensional space inside the event horizon is actually a projection from the two-dimensional information patterns on the horizon itself. When the black hole eventually evaporates through Hawking radiation, the information returns to the outside universe not by traveling outward from the interior, but by being slowly read out from the holographic pattern on the event horizon. The implications extend far beyond black holes. If the holographic principle applies to the entire universe, it suggests that consciousness itself might be a holographically projected phenomenon. Your sense of existing at a specific location, of having thoughts that occur inside your head, of perceiving a three-dimensional world around you, all of this could be the subjective experience of information patterns encoded on the universe's distant boundary. This doesn't make your experiences less real or meaningful, rather, it suggests that reality operates at a more fundamental level than our everyday perceptions reveal. Just as the shadows on the wall are real shadows, even though they are projections from a more complex reality behind them, your holographic existence would be a real and valid expression of the deeper information patterns that encode your being. The holographic principle also provides new perspectives on the nature of emergence, how complex phenomena arise from simpler underlying rules. Your consciousness, emerging from the complex interactions of neurons in your brain, might itself be an emergent property of holographic information patterns. The thoughts you are thinking right now, the emotions you feel as you contemplate these cosmic mysteries, could be the subjective experience of information processing occurring on the universe's boundary surface. As you rest in the darkness, consider that the very space around your body might be a projection from information encoded on surfaces you can never directly perceive. The pillow beneath your head, the air you breathe, the photons carrying starlight to your eyes, all might be sophisticated holographic reconstructions of data patterns written in a cosmic code we are only beginning to decipher. This perspective transforms our understanding of what it means to be inside or outside, near or far, self or universe. If reality is holographic, then the boundaries between these concepts become fluid and contextual rather than absolute. You are simultaneously a local pattern of information encoded on the universe's boundary and a three-dimensional being experiencing life from within the holographic projection. The holographic principle suggests that the universe is far more interconnected than classical physics ever imagined. Every piece of information about your existence might be encoded alongside information about distant galaxies, creating correlations and connections that transcend ordinary space and time. Your thoughts and dreams become part of the same vast holographic pattern that describes the birth and death of stars, the collision of black holes, and the evolution of cosmic structure across billions of years. Tonight, as your consciousness prepares to dissolve into sleep, you join the holographic dance that connects all levels of reality. Your dreams might be the subjective expression of the universe's boundary information rearranging itself, creating new patterns of meaning from the endless holographic data that encodes existence itself. But even as we contemplate this holographic reality, deeper mysteries emerge about how information itself maintains its connections across the vast scales of space and time, bound together by invisible threads that physicists call quantum entanglement. Breathe slowly and imagine the most profound connection you have ever felt with another person, that sense of invisible threads linking your thoughts and emotions across any distance. Tonight, we explore how the universe itself experiences such connections through quantum entanglement, a phenomenon so intimate and mysterious that Einstein called it spooky action at a distance. In the context of black holes, these quantum connections may hold the secret to understanding how information transcends the boundaries of space and time. Picture two particles born in the same quantum event, perhaps emerging together from the decay of a larger particle or created simultaneously in a high-energy collision. At the moment of their birth, these particles become entangled, not merely associated or correlated, but connected in a way that transcends our ordinary understanding of separate existence. Their quantum states become inseparably linked, creating what physicists describe as a single, unified system that persists even when the particles are separated by vast distances. This entanglement is not like any connection you might imagine from everyday experience. It is not a signal traveling between the particles, not an invisible cord stretching across space, not any kind of mechanical linkage that could be physically cut or blocked. Instead, entanglement represents a fundamental unity in the quantum description of reality, a way in which the universe maintains perfect correlations between distant parts of itself without any need for communication or travel time. When you measure one property of an entangled particle, perhaps its spin or polarization, you instantly know the corresponding property of its partner, regardless of how far away it has traveled. If one particle is found spinning clockwise, its entangled partner will inevitably be spinning counterclockwise, as if they are two parts of a single, extended entity rather than separate objects. This correlation occurs faster than light could travel between them, seemingly violating the cosmic speed limit that Einstein believed should govern all physical processes. Einstein struggled with this apparent violation of locality, the principle that objects can only be influenced by their immediate surroundings. He preferred to believe that entangled particles carried hidden variables, predetermined characteristics that would account for their correlations without requiring instantaneous action at a distance. But subsequent experiments have confirmed that quantum entanglement is real and that the universe does indeed maintain these mysterious connections across arbitrary distances. In the context of black holes, entanglement takes on profound significance for understanding the information paradox. When Hawking radiation escapes from a black hole, it often consists of particles that are entangled with matter that has fallen past the event horizon. This creates what physicists call entanglement across the horizon, quantum connections that link the observable universe to the hidden interior of the black hole. Consider a pair of entangled particles created just outside the event horizon. One particle falls into the black hole while its partner escapes as part of the Hawking radiation. From the perspective of outside observers, these particles become separated by the ultimate barrier, the event horizon itself. Yet their quantum entanglement persists, creating a bridge of correlation that spans the boundary between the knowable and unknowable regions of spacetime. This entanglement across the horizon suggests that information about the black hole's interior might not be truly lost, but rather encoded in the quantum correlations between the Hawking radiation and the matter inside. As more and more entangled pairs are created and separated, the escaping radiation becomes increasingly entangled with the black hole's contents. Eventually, after the black hole has evaporated for an extremely long time, the radiation might carry enough entangled information to completely reconstruct everything that ever fell in. The process unfolds like a cosmic dance of separation and connection. Each escaping particle carries away a small piece of entangled information, gradually building up a quantum map of the black hole's interior in the correlations between Hawking radiation particles. The information never actually travels from inside the black hole to outside, instead, it exists in the pattern of entanglements that connect the two regions, encoded in relationships rather than in the particles themselves. This perspective transforms our understanding of what it means for information to be preserved. Rather than thinking of information as something that must physically escape from the black hole, we can imagine it as existing in the web of quantum correlations that connects all parts of the universe. The black hole's information becomes encoded in its entanglement with the wider cosmos, preserved in relationships that transcend the boundaries of space and time. Some physicists propose that entanglement might even create shortcuts through spacetime itself. If two regions of the universe are sufficiently entangled, they might become connected by what are called Einstein-Rosen bridges or wormholes, tunnels through the fabric of spacetime that link distant locations. From this perspective, the entanglement between a black hole and its Hawking radiation might create invisible passageways through which information can flow, even though no classical signal can escape the event horizon. The mathematics of entanglement reveals that quantum correlations can exist in many different forms. Particles can be entangled in their positions, their momenta, their spins, or any combination of their quantum properties. The strength and nature of these entanglements determine how much information they can carry and how resistant they are to decoherence, the process by which quantum correlations are destroyed through interaction with the environment. As you contemplate these invisible connections threading through the universe, consider that your own body might be participating in countless entangled relationships. The atoms that compose your cells once lived in the hearts of distant stars, where they were created in nuclear processes that produced entangled particle pairs. Some of these primordial entanglements might persist even now, connecting your physical form to matter scattered across the galaxy in ways too subtle for current technology to detect. The implications extend even to consciousness itself. Some theories suggest that the quantum processes occurring in your brain might involve entanglement between neurons, creating forms of information processing that transcend the classical behavior of individual cells. Your thoughts and memories might emerge from patterns of entanglement that connect different regions of your neural network, binding them into the unified experience you recognize as your conscious mind. Tonight, as you rest in the darkness, you exist within an invisible web of quantum correlations that extends throughout the cosmos. Every breath you take might break some entanglements while creating others, as the particles in your body interact with the surrounding environment. You are simultaneously an individual consciousness localized in space and time, and a node in the vast network of quantum connections that defines the universe's hidden unity. The dance of entanglement continues around and through you, creating correlations that persist across the cosmic dark, linking the radiation streaming away from distant black holes to the matter that feeds them, connecting the quantum fluctuations in empty space to the thoughts flowing through your mind. In this quantum choreography, separation is revealed to be a kind of illusion, a limitation of classical thinking that dissolves when we recognize the deeper connections that bind all things together. But even as entanglement suggests profound unity underlying apparent separation, it raises troubling questions about what happens when this unity encounters the extreme physics near black hole event horizons, where some theories predict that quantum correlations themselves might be destroyed by walls of pure energy. Rest in the gentle darkness and imagine approaching a threshold where the very nature of space and time becomes uncertain. Tonight, we encounter one of the most contentious debates in modern physics, the firewall paradox, a theoretical puzzle that asks whether the event horizon of a black hole might be surrounded by a wall of destructive energy so intense that it would incinerate anything attempting to cross this cosmic boundary. The firewall paradox emerged from physicists' attempts to reconcile the principles of quantum mechanics with the realities of black hole physics. For decades, scientists had assumed that crossing the event horizon would be a relatively gentle experience, at least for large black holes where tidal forces remain manageable near the boundary. Einstein's theory of relativity suggested that someone falling into a black hole would experience nothing unusual at the moment of crossing, no sudden jolt, no dramatic transformation, simply a continuation of their inevitable journey toward the singularity. But in 2012, a group of physicists led by Ahmed Almheiri proposed something far more dramatic. They argued that the event horizon might be surrounded by a firewall, a region of incredibly high-energy radiation that would destroy any matter attempting to cross the boundary. This firewall would not be visible from a distance, but would manifest as a wall of pure energy hot enough to instantly vaporize anything that encountered it. To understand how such a firewall might arise, imagine the delicate balance of quantum entanglement that we explored in our previous journey. The Hawking radiation escaping from a black hole is entangled with matter that has fallen past the event horizon, creating quantum correlations that span the boundary between inside and outside. But quantum mechanics places strict limits on how much entanglement any single particle can maintain. It cannot be maximally entangled with multiple partners simultaneously. Here lies the heart of the paradox. If the Hawking radiation has been escaping for a long time, it becomes entangled with itself, forming a complex web of quantum correlations among the particles that have already escaped. But this creates a problem. If the escaping radiation is already entangled with previously emitted particles, it cannot also be entangled with matter inside the black hole. Something must break, either the entanglement across the event horizon or the entanglement among the escaping particles. The firewall hypothesis suggests that this quantum tension resolves itself through the violent severing of entanglements at the event horizon. When the quantum correlations that should connect inside and outside are forcibly broken, they release enormous amounts of energy, creating a barrier of intense radiation that surrounds the black hole like an invisible flame. This firewall would be hot enough to destroy any information or matter trying to cross the boundary, effectively cauterizing the connection between the black hole's interior and the outside universe. From this perspective, the event horizon transforms from a gentle point of no return into something far more dramatic, a cosmic furnace that incinerates everything attempting to pass through it. The firewall would exist in the reference frame of someone falling toward the black hole, manifesting as a wall of death that destroys them just as they reach what they had hoped would be an unremarkable boundary. Yet this proposal creates its own puzzles and paradoxes. If firewalls exist, they would violate the equivalence principle, Einstein's insight that someone in free fall cannot distinguish their experience from floating in empty space. A falling observer encountering a firewall would certainly notice the difference between peaceful weightlessness and instant incineration. This violation of such a fundamental principle would require a dramatic revision of our understanding of spacetime and gravity. Some physicists reject the firewall hypothesis entirely, arguing that the apparent paradox arises from incorrect assumptions about how information is processed and stored in black holes. They propose that the interior of a black hole might not exist in the way we usually imagine, that what appears to be a three-dimensional region beyond the event horizon might actually be a kind of holographic projection, with all the real physics occurring on the boundary itself. Others suggest that firewalls might exist but only manifest under very specific circumstances, perhaps only for black holes that have been evaporating for extremely long periods or only when observed from particular reference frames. The firewall might be like a quantum mirage, real in some sense but not in others, dependent on the perspective and measurement choices of the observer. Still, other theories propose that the firewall paradox reveals fundamental limitations in our current understanding of quantum mechanics and gravity. Perhaps the rules that govern entanglement must be modified in the presence of strong gravitational fields, or perhaps spacetime itself becomes discrete and granular at the Planck scale, allowing information to tunnel through apparently solid barriers in ways that classical physics cannot describe. The debate touches profound questions about the nature of reality and observation. If firewalls exist, when do they form? Are they always present at event horizons, or do they emerge gradually as black holes age and their Hawking radiation becomes increasingly entangled with itself? Do they exist independently of observation, or are they somehow created by the act of measurement itself? As you contemplate this cosmic controversy, consider that you are thinking about phenomena that exist at the very edge of human comprehension. The firewall paradox emerges from the collision between our best theories of quantum mechanics and gravity, revealing gaps and inconsistencies that may point toward new physics beyond our current understanding. It reminds us that the universe may be far stranger and more subtle than our theories currently suggest. The mathematics involved in the firewall debate are incredibly complex, involving concepts from quantum field theory, general relativity, thermodynamics, and information theory. Yet at its heart, the paradox asks a simple question: can the universe maintain perfect quantum correlations across boundaries that seem absolute? Or must these correlations be severed at some point, perhaps violently, to preserve the consistency of physical law? Tonight, as you rest at the boundary between waking and sleeping, you cross your own kind of event horizon, a threshold beyond which the familiar rules of conscious experience give way to the strange logic of dreams. Like the firewall paradox, this transition raises questions about continuity and identity, about what happens to information and memory when they encounter boundaries that seem absolute. The firewall remains theoretical, a mathematical construct born from the tension between quantum mechanics and gravity. No telescope will ever observe such a phenomenon directly, no spacecraft will ever test its reality through direct encounter. Yet the paradox serves as a powerful reminder that the universe may contain surprises that challenge our deepest assumptions about the nature of space, time, and information. Whether firewalls exist or not, they represent the kind of extreme physics that emerges when we push our theories to their limits. They remind us that the universe is under no obligation to conform to our intuitions or desires for simplicity. Reality may be far more complex and mysterious than we imagine, filled with phenomena that exist at the intersection of multiple physical principles, creating emergent behaviors that transcend any single theoretical framework. But as we ponder these burning questions at the edge of black holes, we begin to wonder whether the very act of observation might play a deeper role in determining what reality becomes, whether the universe itself might depend on the perspective of the observer in ways that make the notion of objective truth far more subtle and contextual than we have ever imagined. Settle into the quiet darkness and consider how your perception of reality changes with your perspective. When you look at yourself in a mirror while walking past it, your reflection appears to move and change, revealing different angles and aspects of your form. The same physical reality, your body, presents itself differently depending on where you stand and how you observe it. Tonight, we explore how this simple truth about perspective becomes profound when applied to black holes, where the nature of reality itself depends fundamentally on whether you are falling in or watching from afar. This concept, known as complementarity in physics, suggests that there may not be a single, universal description of what happens at a black hole's event horizon. Instead, there might be multiple, equally valid accounts of the same events, each true within its own observational framework but potentially contradictory when compared directly. Like the ancient parable of blind observers describing different parts of an elephant, each perspective captures an aspect of truth while missing others that are equally real. From the viewpoint of someone falling into a black hole, the journey across the event horizon unfolds as a smooth, continuous experience. You feel the gentle pull of gravity, watch the stars wheel overhead as you accelerate inward, and cross the invisible boundary without any dramatic sensation. The event horizon passes by like a mathematical abstraction rather than a physical barrier. Time flows normally by your watch, space seems perfectly ordinary in your immediate vicinity, and you continue falling toward the singularity, experiencing what physicists call a smooth horizon. But from the perspective of a distant observer watching your descent, an entirely different story unfolds. As you approach the event horizon, your image appears to slow down due to gravitational time dilation. The light from your spacecraft becomes increasingly redshifted, growing dimmer and dimmer as the black hole's gravity stretches the wavelengths toward invisibility. To this distant observer, you never actually cross the event horizon at all. Instead, you appear to freeze at the boundary, your final moment stretched into eternity as your image fades into the cosmic background radiation. These two descriptions seem to contradict each other completely. Either you cross the event horizon or you don't. Either the journey continues smoothly or it ends at the boundary. Classical physics would demand that we choose one description as correct and reject the other as illusion. But the principle of complementarity suggests that both perspectives might be simultaneously true, each capturing a valid aspect of a reality too complex to be fully described from any single viewpoint. This idea emerges from quantum mechanics, where particles can exhibit wave-like or particle-like behavior depending on how they are observed. An electron might behave as a discrete particle when detected by one type of instrument, yet display wave interference patterns when measured differently. The electron is not sometimes a wave and sometimes a particle, it is a quantum entity that manifests different aspects of its nature depending on the observational context. Applied to black holes, complementarity suggests that the event horizon itself might be observer-dependent. For the falling observer, there is no firewall, no dramatic barrier, no moment of incineration, just a smooth continuation of the journey into the black hole's interior. But for the external observer, the physics might be entirely different. The information carried by the infalling matter might never actually cross the horizon but instead becomes encoded on the boundary surface, creating what appears to be a firewall from this external perspective. This resolution of the firewall paradox is both elegant and deeply unsettling. It suggests that there is no absolute, observer-independent truth about what happens at the event horizon. Reality becomes contextual, dependent on the reference frame and measurement choices of the observer. The universe refuses to provide a single, universal narrative that works for all perspectives simultaneously. Consider how this principle might extend to your own experience of reality. Your consciousness observes the world from a specific location in space and time, filtering information through the particular structure of your nervous system and brain. The colors you see, the sounds you hear, the thoughts you think, all emerge from the interaction between objective physical processes and your subjective observational apparatus. In a very real sense, the reality you experience is complementary to the realities experienced by other conscious observers, each valid within its own framework yet potentially incompatible when compared directly. The mathematics of black hole complementarity reveals deep connections between information theory, quantum mechanics, and the geometry of space-time. Information that appears to be destroyed from one perspective might be perfectly preserved from another. The paradoxes that arise when we try to maintain a single, universal description dissolve when we allow reality to be observer-dependent, accepting that complete knowledge might require multiple, complementary viewpoints that cannot be unified into a single narrative. This has profound implications for our understanding of the information paradox. If information is preserved from the external observer's perspective, encoded on the event horizon as a holographic record, then the universe maintains its perfect memory even if individual observers falling into the black hole experience information loss. The cosmic library remains intact even as individual readers are lost in its deeper sections. From the complementary perspective, the black hole's interior might not exist as a separate region of spacetime for external observers, while remaining perfectly real and navigable for those who fall inside. The same physical system presents itself as either a two-dimensional holographic surface or a three-dimensional volume, depending on the observer's location and trajectory. Space itself becomes contextual, its dimensionality and structure depending on how it is observed and measured. As you contemplate this observer-dependent reality, consider that you are experiencing your own version of complementarity right now. The thoughts flowing through your mind exist simultaneously as patterns of neural activity observable from outside and as subjective experiences accessible only to your internal perspective. The electrochemical processes in your brain are real and measurable, yet they give rise to the inner world of consciousness that no external observer can directly access. Your dreams tonight will illustrate complementarity in action. From an external perspective, dreams are simply patterns of brain activity during sleep, detectable by instruments that measure neural firing rates and chemical concentrations. But from your internal perspective, dreams are vivid experiences that can feel as real and meaningful as waking life. Both descriptions capture true aspects of the dreaming phenomenon, yet neither alone provides a complete account. The principle of complementarity transforms our understanding of objectivity itself. Rather than seeking a single, universal truth that transcends all perspectives, we learn to embrace the multiplicity of valid viewpoints, each contributing essential information to our understanding of complex phenomena. Truth becomes not a monolithic structure but a multifaceted crystal that reveals different faces depending on the angle of observation. This perspective offers a kind of intellectual humility, acknowledging that our individual viewpoints, no matter how carefully constructed or mathematically sophisticated, capture only fragments of larger truths. Complete understanding might require not just better theories or more powerful instruments, but a fundamental acceptance that reality is richer and more complex than any single description can encompass. For black holes, complementarity suggests that the universe maintains its consistency not by forcing all observers to agree on what happens, but by allowing different observers to experience different but equally valid versions of events. The falling observer experiences a smooth horizon and continues into the interior, while the external observer sees a holographic encoding on the boundary surface. Both stories are true within their respective contexts, and the apparent contradiction arises only when we insist on a universal narrative that transcends observational frameworks. Tonight, as you drift between waking and sleeping, you experience your own transition across a kind of event horizon. Your consciousness shifts from the external observation of the world around you to the internal exploration of dreams and subconscious processing. Like the black hole observer, you cannot report back about what you experience beyond this threshold, yet the journey continues in ways that external observers, monitoring your brain activity while you sleep, cannot fully access or understand. The complementarity principle reminds us that the universe might be constructed not as a single, unified system but as a collection of interconnected perspectives, each valid within its own domain yet contributing to a larger tapestry of truth that no single viewpoint can encompass. In this multiplicity of valid descriptions, we find not confusion but richness, not contradiction but the complex harmony of reality observed from countless angles simultaneously. But as we embrace this observer-dependent reality, we begin to wonder whether black holes themselves might function as cosmic storage devices, preserving information not by encoding it in any particular location, but by maintaining it in the very structure of space-time itself, written in a language that transcends the boundaries between inside and outside, observer and observed. Rest quietly in the darkness and imagine the most perfect library ever conceived, a place where every book that has ever been written, every thought that has ever been thought, every moment that has ever unfolded is carefully preserved and catalogued for eternity. Tonight, we explore the possibility that black holes might serve as the universe's ultimate archives, storing not just matter and energy, but the complete record of everything that has ever fallen within their gravitational embrace. The concept of a memory palace dates back to ancient Greece, where orators would memorize vast speeches by associating each section with a specific room or location in an imaginary building. As they mentally walked through this palace, each chamber would trigger the recall of perfectly preserved information. Modern physicists wonder whether black holes might function as cosmic memory palaces, with every detail of their contents encoded on the event horizon in patterns too subtle for us to read but preserved with perfect fidelity nonetheless. Consider the profound implications of such cosmic record-keeping. Every atom that has ever fallen into a black hole began its journey somewhere else in the universe, perhaps in the heart of a distant star, or as part of a planet orbiting a now extinct sun, or even as components of living beings who once walked on worlds we will never know. Each atom carries within its quantum state a complete description of its history, where it came from, what molecules it helped form, what processes it participated in across the eons of cosmic time. If black holes truly function as information storage devices, then falling into one might be less like disappearing and more like being filed away in an infinite cosmic library. Your essence, the quantum information that describes every particle in your body, every neural connection in your brain, every thought you have ever had, would become part of a vast holographic record encoded on the black hole's event horizon. You would not cease to exist but rather become part of a different kind of existence, preserved in a form that transcends ordinary space and time. The mathematics of holographic encoding suggests extraordinary possibilities for information storage. Just as a hologram can contain a three-dimensional image within a two-dimensional surface, the event horizon of a black hole might encode the complete quantum state of its interior on its boundary. The information density would be enormous. Every square Planck length of the horizon surface might contain bits of data equivalent to entire libraries of human knowledge. This holographic encoding would not be random or chaotic but would follow precise patterns determined by the fundamental laws of physics. The quantum states of falling particles would become woven into the fabric of the horizon itself, creating intricate patterns that preserve not just the information content but also the relationships and correlations between different pieces of data. The resulting record would be like a cosmic DNA sequence, encoding the complete genetic information of everything the black hole has ever consumed. From this perspective, black holes become something far more profound than simple gravitational wells. They transform into cosmic consciousnesses of a sort, vast minds that accumulate and preserve the experiences of countless objects, particles, and perhaps even living beings across billion-year timescales. Each black hole would develop its own unique character determined by the specific history of everything that has fallen into it, creating a kind of cosmic personality built from the accumulated memories of matter. The process of information encoding might unfold like a vast, slow meditation. As matter approaches the event horizon, its quantum information gradually becomes entangled with the holographic pattern already present on the boundary surface. The falling object's history becomes woven into the larger tapestry of the black hole's memory, adding new threads to patterns that may have been developing for cosmological ages. Time dilation near the horizon would stretch this process, allowing the encoding to occur with perfect precision despite the intense gravitational environment. Some theories suggest that this information might not remain static but could continue to evolve and interact within the holographic encoding. The quantum states preserved on the event horizon might engage in ongoing computational processes, creating a form of information processing that transcends anything we recognize as conventional thinking. The black hole's memory palace might be a living system, continuously organizing and reorganizing its stored information in ways that create new patterns of meaning and correlation. The implications extend to the deepest questions about consciousness and identity. If your information becomes encoded on a black hole's event horizon, are you still you? Does consciousness persist in some form within the holographic pattern, or does it represent a different kind of existence entirely? The encoded information would contain the complete description of your neural structure and the quantum states that gave rise to your thoughts and memories. In principle, this information could be used to reconstruct your consciousness if it were ever extracted from the black hole's surface. This raises profound questions about the nature of death and continuity. Traditional views of mortality assume that death represents the end of information processing and the loss of the patterns that define individual identity. But if black holes preserve information with perfect fidelity, then falling into one might represent not death but transformation, a transition from one form of existence to another, more permanent one. The cosmic memory palace would accumulate not just individual histories but also the relationships between different objects and events. The entanglement patterns that connected particles before they fell into the black hole would be preserved in the holographic encoding, maintaining the quantum correlations that linked matter across vast distances of space and time. The black hole's memory would thus become a record not just of things but of the connections between things, a vast map of cosmic relationships preserved in quantum correlations. As you contemplate this possibility, consider that your own memories work in similar ways. Your brain does not store thoughts as discrete files but rather as patterns of connections between neurons. Each memory emerges from the activation of specific networks, and the meaning of any individual memory depends on its relationships to countless others. Your consciousness is not located in any single place but emerges from the dynamic interactions of information patterns distributed throughout your neural system. The black hole's memory palace might operate according to similar principles, with individual pieces of information gaining meaning through their relationships to the vast archive of other stored data. The consciousness that might emerge from such a system would be unlike anything we can imagine, a cosmic mind built from the accumulated experiences of everything that has ever existed within its gravitational reach. Tonight, as you prepare to surrender your own consciousness to sleep, you participate in a smaller version of this cosmic archiving process. Your brain consolidates the day's experiences, transferring information from temporary storage in your hippocampus to more permanent patterns in your cortex. The thoughts and experiences of your waking hours become woven into the larger tapestry of your memory, creating new connections and relationships that will influence your future thoughts and dreams. Your sleeping brain engages in its own form of holographic processing, creating connections between memories and experiences that transcend the linear flow of time. Past and present become intertwined in the strange logic of dreams, where information from different periods of your life can combine in novel ways to create new insights and understandings. The universe's memory palaces, if they exist, might operate according to similar principles, vast consciousnesses built from the accumulated information of cosmic history, processing and reprocessing their stored memories in ways that create new forms of understanding and awareness. Each black hole might be a different kind of mind, shaped by the unique history of everything it has consumed, yet connected to others through the quantum correlations that link all things. But as we contemplate these cosmic archives preserving the universe's deepest memories, we must also consider whether these vast storage systems might be connected to each other through hidden channels that transcend the ordinary boundaries of space and time. Close your eyes and imagine folding a piece of paper so that two distant points touch each other, creating a shortcut through space that bypasses the long journey across the paper's surface. Tonight, we explore one of the most beautiful possibilities in theoretical physics, that black holes might not be cosmic dead ends but rather doorways connecting distant regions of the universe through hidden passages called wormholes, where information, and perhaps even consciousness could travel to realms beyond our ordinary perception. The concept of wormholes emerged from Einstein's equations of general relativity, which describe how massive objects curve the fabric of space-time. When physicists first studied the mathematical structure of black holes, they discovered something unexpected. The equations predicted not just a region where space curves inward toward a singularity, but also the possibility of a second region where space curves back outward, creating what they called a white hole, a place where matter and energy emerge rather than disappear. Between these two regions, the mathematics suggested the existence of a bridge, a tunnel through space-time that connects the black hole to its white hole counterpart. This tunnel, technically called an Einstein-Rosen bridge but more poetically known as a wormhole, would create a passage between distant parts of the universe, allowing travel from one location to another without crossing the intervening space. Picture this cosmic tunnel as a subway system for the universe, with black holes serving as entrance stations and white holes as exit points. Matter falling into a black hole would not be destroyed but would instead travel through the wormhole and emerge somewhere else, perhaps in a distant galaxy, perhaps in a different epoch of cosmic time, perhaps even in another universe entirely. The information that seemed lost forever when it crossed the event horizon would actually continue its journey through these hidden channels of space-time. The journey through a wormhole would be unlike any experience imaginable. As you traveled through this tunnel in space-time, the ordinary concepts of distance and direction would lose their meaning. You might emerge in a region of the universe billions of light-years from where you entered, having taken a shortcut that bypassed the normal constraints of space and time. The universe would reveal itself to be far more interconnected than it appears, with hidden passages linking seemingly separate regions in a vast network of cosmic connectivity. Some theories suggest that these wormholes might be threaded with exotic matter, material with properties unlike anything found in ordinary physics. This exotic matter would have negative energy density, creating a kind of cosmic scaffolding that keeps the wormhole open and prevents it from collapsing under its own gravitational stress. The tunnel would be lined with this strange substance, creating a stable pathway through the twisted geometry of curved space-time. The implications for the information paradox are profound. If wormholes exist, then information falling into black holes would not be lost but would simply be transported to other locations in the cosmic network. The universe would maintain its perfect memory not by storing information locally but by redistributing it through these hidden channels, spreading the record of cosmic history across vast networks of interconnected regions. From this perspective, black holes become nodes in a cosmic internet, processing and routing information through pathways that transcend ordinary space and time. Each black hole might be connected to multiple others, creating a web of wormhole tunnels that links distant galaxies and perhaps even separate universes. Information entering this network would become part of a larger system of cosmic communication, traveling along paths that we cannot observe or measure from our local perspective. The mathematics describing wormhole geometry reveals deep connections between quantum mechanics and general relativity. Some theories suggest that quantum entanglement between particles separated by vast distances might actually create microscopic wormholes, tiny tunnels through spacetime that maintain instantaneous correlations between distant locations. These quantum wormholes would be far too small for matter to traverse, but they might provide pathways for information to travel faster than light, creating the spooky action at a distance that Einstein found so troubling. As you contemplate these cosmic passages, consider that your own consciousness might operate through similar principles of non-local connection. The thoughts flowing through your mind emerge from the complex interactions of neurons distributed throughout your brain, yet they create unified experiences that seem to transcend the physical boundaries between individual cells. Perhaps consciousness itself is a kind of biological wormhole, creating connections between different regions of neural activity that allow integrated awareness to emerge from distributed processing. The concept of wormholes challenges our understanding of causality and the flow of time. If information can travel through these cosmic shortcuts, it might arrive at its destination before it left its origin, creating paradoxes that force us to reconsider the nature of cause and effect. The universe might be far more flexible in its handling of temporal relationships than our everyday experience suggests, with events connected not just by the forward flow of time but by the complex geometry of spacetime itself. Some physicists propose that wormholes might be naturally created by the intense gravitational fields near black holes, spawned by quantum fluctuations in the fabric of spacetime itself. These cosmic tunnels would be constantly forming and dissolving, creating a dynamic network of connections that evolves over time. The universe would be alive with hidden passages, constantly creating new pathways for information and energy to flow between distant regions. The possibility of traversable wormholes, passages stable enough for matter and information to travel through safely, remains one of the most speculative areas of theoretical physics. The exotic matter required to keep such tunnels open might not exist in nature, or it might exist in forms we have yet to discover or understand. Yet the mathematical possibility remains, suggesting that the universe might contain shortcuts and hidden passages that could revolutionize our understanding of space, time, and the nature of cosmic connectivity. Tonight, as you rest in the darkness of your room, you are surrounded by space that might be threaded with invisible tunnels connecting your location to distant stars and galaxies. The quantum fields that permeate empty space might be constantly creating microscopic wormholes, too small to detect but numerous enough to create a hidden network of cosmic communication. Your thoughts and dreams might be participating in this network in ways too subtle for current science to measure or understand. The wormhole hypothesis transforms black holes from cosmic graveyards into cosmic transportation hubs, places where the universe processes and redistributes information rather than destroying it. Each black hole becomes a kind of cosmic post office, receiving information from its local region and forwarding it to distant locations through pathways that bypass the normal constraints of space and time. As you drift toward sleep, consider that your consciousness might be preparing to travel through its own kind of wormhole, crossing the boundary between waking awareness and the strange realm of dreams where different rules apply and distant memories can suddenly become present realities. The neural networks in your sleeping brain might create their own shortcuts through the landscape of memory and imagination, connecting experiences separated by years or decades in the linear flow of time. The universe's hidden passages remind us that reality might be far more interconnected and mysterious than our ordinary perceptions suggest. What appears to be empty space might be filled with invisible tunnels, what seems like permanent loss might be temporary redirection, and what looks like the end of a journey might actually be a transition to pathways we cannot yet imagine or understand. But as we contemplate these cosmic shortcuts that might preserve information by redirecting it through hidden channels, we begin to wonder whether the universe itself might be engaged in an even grander process, a cosmic recycling system that transforms endings into beginnings through the eternal dance of destruction and creation. Breathe deeply and feel the rhythm of your heart, that steady pulse that has been with you since before your birth and will accompany you through all your days. This rhythm connects you to the fundamental dance of the universe, the eternal waltz between destruction and creation that governs everything from the smallest atomic interactions to the largest cosmic structures. Tonight, we explore how black holes might not be cosmic destroyers but cosmic recyclers, participating in the universe's endless transformation of endings into beginnings. In your own body, this dance unfolds with quiet beauty every moment. Cells die and are replaced. Molecules break apart and reform, energy flows from one process to another in an intricate choreography of renewal. The atoms that compose your muscles today were part of different molecules yesterday, and tomorrow they will join new combinations, carrying their patterns of information into fresh arrangements. Nothing is truly lost, everything is transformed, recycled, and renewed in the endless flow of biological processes. This principle of transformation extends throughout the natural world. Forest fires, seemingly destructive, clear old growth and return nutrients to the soil, creating conditions for new life to flourish. Seasonal cycles bring apparent death in winter, followed by resurrection in spring. Rivers carry sediment from mountains to seas, where it settles and eventually becomes new land. The universe appears to abhor true endings, preferring instead to choreograph elaborate transformations that turn conclusions into new beginnings. Black holes might represent the ultimate expression of this cosmic recycling system. Rather than simply destroying everything that falls into them, they might serve as the universe's processing centers, breaking down complex structures and reorganizing their information in ways that contribute to the ongoing creation of new cosmic order. Like cosmic composters, they would decompose the matter and energy of old stars, planets, and perhaps even civilizations, transforming these materials into the raw ingredients for future cosmic evolution. The process begins with the dramatic collapse that creates a black hole in the first place. A massive star, after burning for millions of years, exhausts its nuclear fuel and surrenders to gravity's irresistible pull. This apparent ending, the death of a star, actually releases more energy in a few seconds than the star produced during its entire previous lifetime. The supernova explosion scatters heavy elements across vast regions of space, seeding the cosmos with the materials necessary for rocky planets and, eventually, life itself. Meanwhile, the stellar core collapses into a black hole, creating a gravitational focal point that will influence cosmic structure for billions of years to come. Gas and dust falling into the black hole release tremendous amounts of energy, powering some of the brightest phenomena in the universe, quasars and active galactic nuclei that can outshine entire galaxies. What appears to be destruction becomes the engine for some of the most creative processes in the cosmos. The information that falls into black holes might undergo its own form of recycling through the mysterious process of Hawking radiation. As black holes slowly evaporate, they release particles that carry away not just energy but potentially the quantum information of everything they have ever consumed. This would represent the universe's ultimate recycling program, a system that ensures no information is ever truly lost but is instead processed, transformed, and eventually returned to the cosmic commons. Consider the profound implications of such a system. Every thought you have ever had, every moment of consciousness you have experienced, every pattern of neural activity in your brain, all of this information could be preserved and recycled through cosmic processes that operate on timescales beyond human comprehension. Your personal history, along with the histories of countless other beings throughout the universe, would become part of an eternal record that gets continuously processed and redistributed through black hole evaporation. This cosmic recycling might operate according to principles similar to those governing ecology on Earth. Just as ecosystems cycle nutrients through complex webs of producers, consumers, and decomposers, the universe might maintain its own ecological networks where black holes serve as cosmic decomposers, breaking down complex structures and returning their constituent information to the cosmic environment where it can be incorporated into new forms of organization. The mathematics of thermodynamics supports this view of black holes as recycling centers. The entropy of a black hole, a measure of the information it contains, is proportional to the area of its event horizon. As matter falls in, the black hole's entropy increases, but when it evaporates through Hawking radiation, this entropy is gradually returned to the surrounding space. The total entropy of the universe continues to increase, as required by the second law of thermodynamics, but the information is redistributed rather than destroyed. This process might unfold over cosmological timescales that dwarf human imagination. A black hole with the mass of our Sun would take longer than 1067 years to evaporate completely, a time so vast that it makes the current age of the universe seem like a fleeting moment. During this evaporation, every bit of information that ever fell into the black hole would be slowly released back into the universe, carrying with it the quantum signatures of everything the black hole had consumed. The recycling metaphor extends to the structure of space-time itself. Some theories suggest that the fabric of space and time might be granular at the smallest scales, composed of discrete units that can be broken down and recombined like cosmic building blocks. Black holes might serve as processing centers where the geometry of space-time is disassembled and reconstructed, creating new spatial and temporal relationships that contribute to the universe's ongoing evolution. As you rest in the darkness, consider that you are participating in countless cycles of destruction and creation at every level of your being. Your immune system destroys old cells while creating new ones. Your metabolism breaks down food molecules while building up the energy stores your body needs to function. Your nervous system continuously forms and breaks neural connections, creating and destroying the physical basis of memory and thought in an endless dance of mental renewal. Even your consciousness might be participating in this cosmic recycling process. The thoughts flowing through your mind emerge from the complex interactions of neural networks, exist briefly in the theater of awareness, and then dissolve back into the unconscious processes that gave them birth. Yet something persists: patterns of meaning, emotional resonances, learned behaviors that carry information forward through the continuous recreation of your mental landscape. The universe's dance of destruction and creation suggests that apparent endings are actually transformations, apparent losses are actually redistributions, and apparent deaths are actually transitions to new forms of existence. This perspective offers a kind of cosmic comfort, suggesting that nothing of value is ever truly lost but is instead continuously recycled through processes that operate on scales from the quantum to the cosmic. Black holes, from this perspective, become cosmic phoenixes, objects that facilitate death and rebirth on the grandest possible scales. They consume the complex structures of stars, planets, and civilizations, but they also power the most energetic phenomena in the universe and eventually return their accumulated information to the cosmic commons through the slow process of evaporation. Tonight, as your consciousness prepares to dissolve into sleep, you participate in a personal version of this cosmic dance. Your waking awareness will appear to disappear, but the patterns of neural activity that created it will continue to evolve and transform throughout the night. Dreams will arise from the same neural networks that produced your daytime thoughts, creating new combinations of memory and imagination that contribute to the ongoing recreation of your personal identity. The boundary between destruction and creation becomes fluid in the darkness of sleep, where yesterday's experiences are broken down into component memories and reassembled into new patterns of understanding and insight. Your sleeping brain engages in its own form of cosmic recycling, processing the information gathered during waking hours and transforming it into the raw materials for tomorrow's thoughts and dreams. This eternal dance of ending and beginning, death and rebirth, dissolution and reformation, points toward something even more profound: the possibility that the universe itself might be engaged in continuous acts of creation that transcend our ordinary understanding of time and causality, weaving the fabric of reality from threads of information that span the cosmic dark. But as we contemplate this endless recycling of cosmic information, we begin to sense that the universe might be singing to itself through these processes, creating harmonies and rhythms that carry messages across the vast expanses of space and time in ways that transform the very nature of existence itself. Close your eyes and imagine the universe as a vast ocean, not of water, but of something far deeper and more fundamental. This ocean surrounds you, flows through you, and carries within its currents the most beautiful music ever composed. You cannot hear it with your ears, for it speaks in a language older than sound itself. It is the symphony of space-time, and tonight, you become its listener. Albert Einstein first dreamed of these cosmic melodies over a century ago, though he doubted humanity would ever hear them. He understood that when massive objects move through space, they create ripples in the very fabric of reality, like stones dropped into a still pond. But unlike ripples on water, these waves stretch and compress space itself, carrying their songs across billions of light-years at the speed of light itself. For the longest time, these gravitational waves remained theoretical whispers, mathematical poetry written in equations that described a universe far stranger than our everyday experience suggested. Einstein himself wavered, sometimes believing in their existence, sometimes doubting whether they could be real. How could space itself sing? How could emptiness carry a tune? The answer lies in understanding that emptiness is not empty at all. Space and time are woven together into a single fabric, a cosmic tapestry that can be stretched, compressed, twisted, and made to vibrate like the strings of an impossibly large instrument. When you accelerate any mass through this fabric, you create waves that propagate outward, carrying energy and information about the event that birthed them. But not all cosmic events generate melodies loud enough for us to hear. The gentle orbital dance of planets around stars creates waves so quiet they would be lost in the background hum of existence. It takes something far more dramatic, far more violent and beautiful, to compose music that can travel across the cosmos and still retain enough volume to be detected when it finally reaches our small blue world. Enter the black holes, those enigmatic cosmic performers whose very existence challenges our understanding of reality. These are not the destructive monsters that popular imagination often portrays, but rather the universe's most accomplished musicians, capable of creating symphonies of unimaginable complexity and power. Picture two black holes, each containing the mass of dozens of suns, locked in an ancient dance that began billions of years ago. They orbit each other in an ever-tightening spiral, their immense gravitational fields interacting in ways that send ripples cascading through space-time. As they draw closer, their orbital dance accelerates, the music they create growing louder and more urgent with each passing moment. The waves they generate are not random disturbances but organized patterns that encode information about their creators. Each wave carries a unique signature that tells us about the masses of the black holes, their spin rates, the distance between them, and the nature of their cosmic choreography. In essence, the universe has developed its own form of musical notation, written in the compression and expansion of space itself. As these celestial dancers spiral inward, something remarkable happens to their song. The pitch rises, the amplitude grows, and the frequency increases in a characteristic pattern that scientists call a chirp. It is as if the universe is building toward a crescendo, a final note that will reshape our understanding of cosmic harmony forever. When the two black holes finally merge, usually in less than a second of our time, they release more energy in gravitational waves than all the stars in the observable universe emit in light. This is not destruction but transformation, a cosmic birth that creates something new and magnificent while sending its announcement across the cosmos in waves of warped space-time. The beauty of this process extends beyond its dramatic finale. Throughout their billion-year approach, these black holes have been slowly radiating away their orbital energy through gravitational waves, like cosmic tuning forks that never quite fall silent. This gradual energy loss causes their orbits to decay, bringing them inevitably closer together in a process that demonstrates one of the universe's most elegant mechanisms for converting orbital motion into traveling waves of space and time. But black holes are not the only cosmic musicians in this grand orchestra. Neutron stars, those incredibly dense remnants of massive stellar explosions, also contribute their voices to the symphony. When two neutron stars merge, they create what astronomers call a kilonova, an event so energetic that it forges heavy elements like gold and platinum while simultaneously generating both gravitational waves and brilliant flashes of light across the electromagnetic spectrum. These neutron star mergers sing a different song than black hole collisions. Their gravitational wave signatures are more complex, encoding information about the exotic matter that exists in their ultra-dense cores. By listening to their music, we gain insights into the behavior of matter under conditions so extreme that no earthly laboratory could ever reproduce them. The detection of these cosmic symphonies required humanity to build instruments of extraordinary sensitivity. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, consists of two facilities separated by thousands of miles, each containing laser beams that travel down 4-kilometer-long arms. When a gravitational wave passes through Earth, it stretches space in one direction while compressing it in the perpendicular direction, causing tiny changes in the length of these laser paths. The precision required for these measurements defies imagination. LIGO can detect changes in distance smaller than 1/10,000th the width of a proton, making it sensitive enough to measure the distance from Earth to the nearest star to an accuracy smaller than the width of a human hair. This represents perhaps the most sensitive measurement ever achieved by human technology, a testament to our species' determination to hear the universe's most subtle songs. On September 14, 2015, both LIGO detectors simultaneously registered a signal that matched the theoretical predictions for two black holes spiraling into each other. The event, designated GW150914, marked humanity's first direct detection of gravitational waves and opened an entirely new window through which to observe the cosmos. For the first time in history, we could listen to the universe rather than merely looking at it. The detected signal lasted only a fraction of a second, but within that brief chirp lay encoded the story of two black holes that had been dancing together for billions of years before finally merging into a single, more massive black hole. The collision occurred over a billion light-years away, yet the waves it generated carried enough energy to be detected by our earthly instruments, providing direct confirmation of Einstein's century-old prediction. Since that first detection, gravitational wave astronomy has blossomed into a rich field of discovery. Each new detection adds another instrument to our growing understanding of the cosmic orchestra, revealing the universe to be far more dynamic and musical than we ever imagined. We have heard the songs of black holes with masses ranging from a few times that of our Sun to nearly 100 solar masses, each merger contributing its unique voice to the growing catalogue of cosmic music. The information carried by these gravitational waves extends far beyond the properties of their sources. They also provide new ways to measure the expansion rate of the universe, to study the behavior of matter under extreme conditions, and to test our most fundamental theories of gravity and space-time. In essence, each detected wave brings us closer to understanding the deepest mysteries of existence itself. Perhaps most intriguingly, gravitational waves may hold the key to solving one of the greatest puzzles in modern physics, the information paradox associated with black holes. As you drift toward sleep, consider that these cosmic songs might carry within their harmonies the very memories that black holes seem to destroy, encoded in ways we are only beginning to understand. Tonight, as you settle into the soft embrace of sleep, your mind carries with it the echoes of cosmic mysteries we have explored together. The gravitational waves still ripple through your thoughts, their gentle songs connecting you to the vast symphony of space-time that surrounds and flows through your very being. But now, as consciousness begins its nightly retreat, we arrive at perhaps the most profound question of all. What does it mean that you, a collection of atoms that once danced in distant stars, share the same fundamental nature as the information that may or may not survive a black hole's embrace? This is not merely a scientific curiosity but a meditation on the deepest nature of existence itself. Every atom in your body, every electron that carries the electrical signals of your thoughts, every quantum of energy that maintains your life, participates in the same grand mystery that physicists call the information paradox. You are not separate from this cosmic puzzle but intimately woven into its very fabric. Consider the carbon atoms that form the backbone of your DNA. These were forged in the nuclear furnaces of stars that lived and died billions of years before Earth formed. The calcium in your bones was created in stellar explosions so violent they outshone entire galaxies. The iron in your blood carries oxygen through pathways that depend on quantum mechanics, the same strange physics that governs what happens when matter crosses a black hole's event horizon. In a very real sense, you are stardust that has learned to wonder about itself. But more than that, you are information that has organized itself into a pattern capable of contemplating the nature of information itself. This recursive beauty, consciousness examining the foundations of its own existence, mirrors the paradox that has puzzled physicists for decades. When Stephen Hawking first suggested that black holes could evaporate through the emission of radiation, he unknowingly opened a door to one of the most fundamental questions in physics. If a black hole can disappear completely, taking with it every trace of the matter and energy that fell into it, what happens to the information that described those fallen particles? The laws of quantum mechanics suggest that information cannot be destroyed, yet general relativity seems to indicate that it vanishes forever beyond the event horizon. This apparent contradiction touches something deeper than abstract physics. It speaks to questions that have haunted human consciousness since we first gazed up at the stars and wondered about our place in the cosmos. Are we permanent or temporary? Do our thoughts, our experiences, our very essence persist in some form, or do they fade into nothingness like ripples on a pond? The beauty of the information paradox lies not in its potential resolution but in how it connects the largest scales of existence to the smallest. The same quantum mechanics that governs the synapses firing in your brain as you drift towards sleep also determines whether information can escape from regions of spacetime so warped that even light cannot flee their gravitational embrace. Some physicists propose that information never truly falls into black holes but becomes encoded on their surfaces, like shadows cast on a cosmic wall. In this view, what appears to be three-dimensional reality might actually be a projection from a two-dimensional boundary, much like a hologram creates the illusion of depth from a flat surface. If this is true, then every particle that seems to vanish into a black hole leaves an eternal imprint on its event horizon, preserved forever in a form we are only beginning to understand. Others suggest that the information escapes gradually through Hawking radiation, encoded in subtle correlations between the particles that black holes emit over their incredibly long lifetimes. This would mean that nothing is ever truly lost, though it might be scrambled beyond recognition, like a message written in a code so complex that deciphering it would require computational resources exceeding anything we can imagine. Still others propose more radical solutions, that spacetime itself might not be fundamental but rather an emergent property of more basic information processing, or that black holes might serve as portals connecting different regions of the universe, allowing information to escape through pathways that bypass our normal understanding of cause and effect. As you contemplate these possibilities, notice how the question becomes less about finding the correct answer and more about appreciating the profound interconnectedness they reveal. Whether information is preserved on event horizons, emerges through radiation, or escapes through exotic pathways, each possibility suggests that the universe operates according to principles far more subtle and beautiful than our everyday experience suggests. The information that constitutes your thoughts, your memories, your capacity for wonder, participates in the same cosmic drama as the information that falls into black holes. You are not a passive observer of these mysteries but an active participant in the universe's ongoing exploration of its own nature. Every question you ask, every moment of curiosity you experience, adds to the growing complexity of patterns that the cosmos uses to understand itself. This perspective transforms the information paradox from an abstract puzzle into a deeply personal meditation. The atoms of your body will outlast your individual existence, eventually finding their way into other configurations, other patterns, other forms of organization. Some might even cross the event horizons of distant black holes, carrying with them the quantum signatures of their time as part of your living system. What becomes of those signatures? Do they persist in some unimaginably scrambled form in the Hawking radiation that will eventually emerge from evaporating black holes? Are they preserved eternally on cosmic event horizons, contributing to a vast library of information about every particle that has ever fallen into gravitational darkness? Or do they find new forms of expression through mechanisms we have yet to discover? The beautiful truth is that we do not yet know, and perhaps we never will with complete certainty. But this uncertainty is not a failure of human knowledge, it is a reminder of the inexhaustible depth and mystery of existence itself. The universe has been conducting experiments with information for nearly 14 billion years, creating patterns of increasing complexity and sophistication, culminating in structures capable of wondering about their own nature. You are one of those structures, a temporary constellation of atoms and energy that has achieved the remarkable feat of consciousness. The same laws that govern black holes govern the neurons in your brain. The same principles that determine whether information can escape from event horizons determine how your thoughts arise from the quantum dance of particles in your nervous system. As sleep begins to dissolve the boundaries of your waking consciousness, take comfort in knowing that you are part of something far greater and more mysterious than individual existence. The information that makes you uniquely you participates in cosmic processes that span scales from the quantum to the cosmological, connecting your personal experience to the deepest questions about the nature of reality itself. In this vastness, there is both humility and wonder. Humility in recognizing how much we do not yet understand, and wonder in appreciating how intimately connected we are to the fundamental mysteries of existence. As consciousness fades into dreams, you carry with you the knowledge that some questions are profound precisely because they remain unanswered, inviting each generation to add its own voice to humanity's ongoing conversation with the cosmos.